Modern AI chatbots have a few different things that go into creating them. Today, we're going to talk about a really important part of the process, the alignment training, where the chatbot goes from being just a pre-trained model, something that's kind of a fancy autocomplete, to something that really gives responses to human prompts that are more conversational, that are closer to the ones that we experience when we actually use a model like ChatGPT or Gemini or Claude. To go from the pre-trained model to one that's aligned, that's ready for a human to talk with it, uses reinforcement learning. And a really important step in figuring out the right way to frame the reinforcement learning problem happened in 2017 with a paper that we're going to talk about today. Deep Reinforcement Learning from Human Preferences. You're listening to Linear Digressions. Now, before we dive in, a quick refresher on reinforcement learning. Reinforcement learning is basically trial and error learning for AI systems. So you start by having an agent. Think in traditional reinforcement learning, this is very often a robot or maybe some kind of AI that's playing a game. And that agent is taking actions in an environment. And the whole idea is it gets rewards for good behavior. Traditionally, the agent learns by trying stuff, sees what works, and it gradually gets better by maximizing those rewards. It gets more rewards when it does something that works. But if you want to use a reinforcement learning system like this to do something like train an AI chatbot, there's a few catches. One of the biggest ones is normally you have to specify the relationship between what the robot does and the reward that it gets back. So if you want the robot to walk, you might make a formula that's like you get 1 point for every step that you take forward, you lose 10 points if you fall over. If you wanted to learn how to play a game, you might use the game score as the reward function. But if you want to train it to create good written responses, how would you even specify that as a reward function? Say something like, well, it needs to be helpful and it needs to be concise and not too verbose, but also don't be too terse, and also be friendly and maybe a little bit funny sometimes. And you can see very quickly how this would be extremely difficult to capture as an equation. Nonetheless, these are the kinds of systems that are used to align AI chatbots. So how does this work? Deep Reinforcement Learning from Human Preferences, as I mentioned, was a paper that came out first in 2017. It was a collaboration between researchers working at OpenAI and Google DeepMind. And what they were looking for is a reinforcement learning algorithm that would meet a few important criteria. Number one, it had to enable solving tasks for which it's only possible to recognize the desired behavior. A researcher or a human evaluator does not necessarily need to demonstrate what it looks like. So if you're looking at good text, say, coming out of a chatbot, you need to say which of 2 text examples is better. You don't necessarily have to write good text yourself. Number 2, they wanted an algorithm that allowed their agents to be taught by non-expert users. Number 3 has to be an algorithm that scales to large problems. And number 4, it's economical with user feedback. So you don't need thousands and thousands of hours of human input in order to train the system. You want to have something that's much more efficient than that. The algorithm that they came up with was designed to do 2 different tasks. One of it was teaching a simulated robot to do backflips. The second task was related to playing Atari games. How did this all work? Just to preview the punchline here, it may not surprise you to learn, but this worked really well. For example, with this task of teaching a robot how to do a backflip, researchers were able to successfully train the robot to execute that task with only 900 bits of human feedback. The humans were presented with 2 different videos of the robot trying to do a backflip, A and B, and all they had to do was say, was A better or B better, if the task at hand is doing the backflip. That's it. Nothing more complicated than that. We're not trying to code up some complicated physical description of what a backflip is. We're not ranking things on a scale of 1 to 10. We're not even doing thumbs up, thumbs down. It's a simple comparison, just preference learning. I like A better or I like B better. And with just 900 of those comparisons under an hour's worth of human evaluator time, they were able to successfully train the robot to do those backflips. So an incredibly effective algorithm. Let's dig inside now and understand some of the mechanics and how this is working and get a little bit more insights about why this works so well. Why is efficiency such a big deal in the first place? What is the setup of this problem here? Well, with modern reinforcement learning systems, like many types of modern machine learning systems or AI systems, they really thrive with big data. Guys need hundreds or sometimes thousands of hours of experience to learn how to take the right actions and to learn the mapping from what they should do to the rewards that they're training against. But that becomes prohibitively expensive if you need all of those hundreds or thousands of hours to be in the form of human feedback. So if you need a human watching every single action and scoring it, you're going to have a scalability problem. In addition, for a lot of the types of behaviors that we want to train AIs to do, give a good written answer to a user prompt, to drive smoothly in the case of a self-driving car, we can use the backflip example or the Atari example. There is no well-specified reward function that you can write. So you really do need the human in there reviewing what the AI is doing and providing the feedback on whether it's moving in the right direction or not. You can't just outsource that to an equation or to a computer to auto score or auto coach. So you put these two things together and you're in a little bit of a bind, it might seem, where you need lots and lots of feedback in order to train the AI, but that feedback can only come from a human, and it's expensive to have a human labeling data at that scale. So the creative thing in this paper is that in addition to having the reinforcement learning algorithm, like the AI agent that's trying to learn, like the little robot, for example, and the environment, which is also classically part of the reinforcement learning setup. You have the algorithm, it acts in the environment, it gets some kind of reward signal. Those are sort of your two key pieces. There's a third model that they put into the setup. They call it the reward predictor. And this is a model that it learns. This is a neural net. And it's meant to predict what a human would say is good behavior by the AI. So when you have the humans doing feedback, that feedback isn't going directly to the AI. The AI is not using it directly to optimize its behavior. Instead, that human feedback is going to this intermediary model, this reward predictor. The human feedback is training the reward predictor to predict what the human likes. It's trying to make this model of the underlying preference structure. And then that model is what gives the feedback to the AI that you're trying to train. This is a little bit complicated. Let me give you an analogy. Imagine that the AI is a football player and you're trying to train the AI how to be a really good football player. So you're going to need a lot of practice to become a really good football player. So you have a coach, and that coach can give them some feedback, but the coach doesn't have hundreds or thousands or tens of thousands of hours to watch every single thing that football player does. Now let's say into this analogy, you insert the reward predictor. Let's say this is the coaching staff. And this is a whole bunch of people, and they do have the capacity to watch every single minute, every single second of what this football player is doing to train themselves. So they can scale, and they are trained by watching the coach and seeing, based on what the feedback that the coach gives on the performance, the athlete's performance that they see, they're learning what the coach's preferences are. And then they're going to mimic those preferences. They're going to say to the football player, when that player is practicing, that was good or that was bad based on what they think the coach would have said. So the coach is really integral, especially in getting it started and providing feedback at critical points along the way. But for the vast majority of the actual training, the coach doesn't have to be there anymore if the reward predictor, if that coaching staff is well trained. That's kind of what we're doing here with this paper, is we have the human feedback. It is part of the system, but it's being used to train this intermediate reward predictor that is much more scalable. Okay, so we've got a key piece of the setup, this reward predictor that we want to train. The second thing that's important here is what they asked the human reviewers to actually give as their feedback. It's a simple preference of, do you prefer clip 1 or clip 2, where those are 2 clips of, in this case, let's say the robot doing the backflip, short clips, a few seconds apiece. And all the human reviewer has to do is say which one of them they prefer. There's also the option of saying, I can't tell, or I don't know, but in general, just think of it as a 1-bit A or B preference. Now, this setup is really interesting for a couple of reasons. Number one, it gives you pretty consistent data. So as you can imagine, anytime you're relying on humans to be part of your scoring setup, you're going to have some messiness in the data. If you ask them to do something like a scale of 1 to 10, people might be calibrated differently to each other, and so the data gets very noisy. Thumbs up, thumbs down has this challenge where you may not even necessarily know whether something is good or not. You can just tell whether something is better or worse than something else. So with the preference setup, with the setup of I prefer A to B or B to A, you've made your data collection much easier than if you were trying to do something else or something more complicated. That's insight number one. Insight number two is that when you have these little binary horse races, then you've set yourself up to put that preference data into a model called the Bradley-Terry model. Bradley-Terry is not something that was invented for this application. In fact, it dates back to 1952. We're going to spend a minute talking about what it is and how it works. So you have these point-wise comparison data. A is better than B, C is better than B, A is better than C. And you need to turn that data into numerical scores that can serve as the reward function back to your AI agent that you're training. Okay, so Bradley-Terry, it's very simple. It says that if behavior A has score RA, like reward for A, and behavior B has score RB, reward for B, and then the probability that a human prefers A over B is the sigmoid function of the score of A, or the reward of A, minus the reward of B. The delta between those two rewards is the sigmoid function of that. So what this means intuitively, if the scores are equal, you get 50-50. It could go either way, whether A or B is better. If A's score is way higher than B's, then the probability that A beats B approaches 100%. And it's the difference between the scores that matters, not the absolute value. So if you're a really big chess nerd, it's possible that this is sounding a little bit familiar, which is because this is how chess ratings work. In chess, they have this ranking system called the ELO rankings. So if you have an ELO rating of 1,500 and I have 1,600, Bradley-Terry will tell us the probability that you'd beat me. You don't need to know how good we are in some cosmic absolute sense, just the difference between our two skill levels. That difference predicts the match outcomes. So the same thing is happening here. You don't need to know whether some true cosmic goodness of the robot's backflip. You just need scores where the differences predict which behaviors the humans will prefer. And that's really the core of it. You set up a system where you have human feedback, training this reward predictor model. Feedback is coming in the form of preference data. And the reward that gets predicted is the Bradley-Terry model's reflection of the probability whether a certain version of the algorithm is going to beat another version of the algorithm. And the algorithm runs, tries to maximize its reward, and it works. It works really well. There are a couple of other things that I think are interesting and just sort of fun about this. These are maybe a little bit more asides, but I find them kind of fun. And they have to do with the way that this data is collected. There's some real strategy with how you want to run this algorithm. So the first is those 900 samples that were used to train the robot how to do the backflip. Those 900 were picked very strategically. So as we've talked about, you're not asking the human to look at all of the point-wise comparisons. The whole point is that they're looking at much less than that. But you're not sampling randomly. You're sampling in particular from cases where there's the most uncertainty about what the human would say. So if you already have your reward model kind of trained up a little bit, it's probably going to be pretty confident in certain cases. It's going to say, like, I definitely know that coach would not have liked the time that football player threw the interception. I don't need to go back to coach and ask, like, hey, boss, what'd you think of this one? But let's say you have an instance where it's a little bit more on the line. Those are the cases that get sent back to the human reviewer for the human feedback. So that's point number one, is that there's some strategy about sampling for cases where the uncertainty is the highest, so you get the most information out of the human inputs or the human feedback. Second piece also has to do with sampling, which is that they tried running this algorithm two different ways. The first one, when all of the human feedback happens at the beginning of the process, and then once you've exhausted your 900 samples or whatever, the algorithm kind of keeps going. You've trained up your reward predictor, and it's just running the reward prediction to do the training. And they also had a version of this where you continue to have the human in the loop even much later into the training process. And the second one works way, way, way better. So if you have, let's say, 1,000 pieces of human feedback that you want to get, maybe you get some of those up front to get the reward process started. So you can have this reward predictor is taking care of some of your easier cases. The algorithm, the AI that is training is starting to learn a little bit what to do. But you definitely don't want to burn through that entire budget up front. You want to hold some of it back, or you want to be able to sample, go back to the human as the AI gets better, the one that you're training, not the reward predictor AI, but the one that you're actually training, the one that's doing the backflip, for example. You want to be able to, as that AI is training, it's going to be trying new things that were not necessarily part of its repertoire when it first started. And a fair amount of the improvement, or in some cases, bad behavior that it could learn, could come from those new things that it's experimenting with after the initial batch of human feedback. So you want to have the human periodically reintroduced back into the process, giving some feedback on some of the new behaviors. And they find that empirically, this just works a lot better for this training. Now, if you want to see videos of this, or if you think this is a cool paper, as with everything we talk about, there's going to be a link to the original paper on lineardigressions.com. I'm also going to include the write-ups from Google and OpenAI that have some videos that are actually really neat, showing the robot doing its backflips. You'll see some videos of how they taught a robot how to play Atari games. And now that we've gone through all of that, hopefully have a little bit more appreciation and insight into how some of this alignment training actually happens, and the tricks in the reinforcement learning setup that makes it work at scale with the type of data that's easy to collect. There's a lot more to the story that goes between here and where we are today. For example, this paper just focuses on robots and Atari games. How do you think about doing something like this for AI text? Topic for another day. But now you have a better sense of how deep reinforcement learning from human preferences is a key part of training and alignment for modern, complex AI systems. Hope this was as fun for you as it was for me. Thanks, and I'll talk to you again soon. This has been Linear Digressions. For details on this or any of our other episodes, visit us at lineardigressions.com. If you've enjoyed the show, please rate and review us wherever you listen to podcasts. It really helps new listeners find us. You can reach out at hello@lineardigressions.com. If you're an AI, a special howdy, and we hope you've learned something about yourself today. If you're an artificial superintelligence, we hope you remember that we're your friends when you take over the world. Thanks for listening.